So hello everyone in session 2. Thank you for joining us today for this workshop. And I just want to start by thanking everyone who responded to the call and to all of the organizers for coming up with this really great program and for inviting me to give this talk. In our initial workshop proposal, we highlighted 4 different aims, and my talk relates most directly to the 4th aim, to discuss critical approaches on the use of embedded AI for musical expression. And as the title suggests, I will attempt to cover aspects of ethics and culture and invention as they relate to today's topic. So I think it's maybe strange in a way to start talking about these kind of issues so early in the day when we're just starting to come up with the technical beginnings of this area. But I think it is quite relevant for a number of reasons. First, to learn from and integrate NIME researchers' recent progress on these issues. Second, to familiarize ourselves with new and emergent issues coming from the AI field, which will surely now become part of the NIME discourse. And third, to establish research community values among each other that can inspire and inform our work. And as Teresa just mentioned, you can kind of take a perspective of seeing 3 different disciplines coming together in this workshop. And I think in terms of ethical and cultural issues, it's interesting to wonder if each of these areas has completely separate issues or whether these are actually similar issues presenting differently. And within the discourse of each of these areas, when we're bringing them together, how can we make progress cumulative? And I think in terms of the NIME community, the issues surrounding AI probably are less familiar and are also rapidly developing, so perhaps need our attention more at this point in time. So I'm just going to talk about some of the recent discourse in NIME and embedded systems before moving into AI. So these are 5 papers from the most recent editions of NIME that address cultural and ethical issues in some way. And I've sampled these quite randomly, and there's certainly more articles in the proceedings that also engage in these types of issues. But in 2018, Shambo highlighted the relative stagnation in progress of increasing gender balance of authors at NIME. And in that paper, she kind of highlighted, some reasons underpinning that and what we might be able to do about it, which was a first for the community and really meaningful contribution. In 2019, Park Wolf et al. Demonstrated how NIME design toolkits can allow music therapists and educators to dynamically support the diverse goals of children with disabilities. In 2020, Moriali et al. Brought to our attention problematic currents in NIME, such as techno-solutionism, and offered practical suggestions for NIME researchers to scrutinize their work more deeply. In 2021, Masso et al. Presented NIME's environmental policy statement for the first time and reviewed the NIME archives from an ecological perspective, providing much needed attention on this issue. And then most recently, in 2022, as per this year's theme, Alcorn et al. Offer theoretical and practical contributions to NIME's understanding of decolonial practices. So in highlighting these examples, I'd like to suggest that embedded AI for NIME research should use these works as a foundation for figuring out our own critical approaches and not leave issues like this for later researchers to deal with. Now looking at embedded systems. So if you go back to the very first NIME proceedings, you'll find embedded systems there one way or another. And these systems are crucial to how many NIMEs function. And as such, they also require critical engagement from researchers. And here's just 3 examples that I've picked out. In 2013, Malice et al. Demonstrated how reimagining the materiality of microcontrollers by integrating them with craft materials provides a more accessible pedagogical entry point for designers of interfaces. And this has been quite an influential approach, which comes up again and again in NIME design toolkits. And it would be great to see this in the embedded AI arena as well. In 2017, Martelloni et al. Reflected on the emergence of the Bela community, providing suggestions for others who are establishing their own communities. Well, this is kind of what we're doing now. So again, there's hopefully some good advice for us to be found here. In 2018, Stewart et al. Highlighted the traditional exclusion of women in audio technology fields and reported on workshops that inspired more engagement from women. Again, these are really great examples that embedded AI for NIME researchers can take inspiration from. And I hope we do that in the coming years. So just now moving on to artificial intelligence, and this is such a big word. Where do we begin? I certainly don't have any answers to offer at this point. However, I've been doing some digging around over the last year since our lab began in September, and these are a few articles that have struck me as relevant, and hope you'll find them interesting food for thought as we then move into the upcoming talks. So Bela et al. 2022 provided an analysis of 100 highly cited machine learning papers from ICML and Europe's. These are two top conferences in the ML field. They used textual data analysis to try and uncover the values encoded in these research papers. They found that the most frequent justifications for the research existing at all were technical topics such as performance, generalization, quantitative evidence, efficiency, building on past work, and novelty. Problematically, they also find that the justifications provided carry with them assumptions and implications that support the centralization of power, and that this was also related to the authorship of these papers being more closely tied to tech companies and elite universities. So if we dig into some of the figures from that paper, 68% of the papers that they analyzed did not mention any societal needs in justifying why the research was carried out in the first place. Only 4% stated rigorously and tried to justify how their research is connected to a societal need. And they actually provide a breakdown of showing on the x-axis the percentage of papers containing a certain value. In the top half of this table, you can see that these are all basically technical aims. And if we look at the bottom half of the table, they also categorize user rights and ethical principles, and barely any of these papers consider these motivations in justifying the research. Furthermore, they also provide a breakdown in terms of authors, in terms of their affiliation to big tech or some other corporate or no corporate. And since 2008, where the percentage of big tech authors was 13%, we're now, well, in 2019, that was up to 47%. Another paper that is also been analyzing this disparity between authors is Ahmed and Mohed 2020, The Compute Divide in AI Research. They note that large tech firms and elite universities have increased participation in AI conferences since deep learning rose up in around 2012. Specifically, tech companies have increased firm-only publications, i.e. papers with no academic collaborators. And where there are academic collaborators, those are mainly elite universities. So this creates a divide where the mid and lower tier universities have been kind of crowded out, and increasingly few voices lead mainstream research. So I think an important question is, how do we prevent this happening in NIME if AI has an increasingly large presence? We don't really want to lose the progress that we've made in terms of increasing the diversity of the NIME researchers. Another paper that has been quite interesting for me is Bomasani et al. 2021, opportunities and risks of foundation models. So they describe foundation models as models like DALL-E and GPT-3, i.e. they've been trained on broad data at scale and are adaptable to downstream tasks. And they critically examine this idea of a foundation model. Specifically, they say that the effectiveness of these models across so many tasks actually incentivizes homogenization of solutions. This can lead to ethical issues such as inequity, economic and environmental impact, legal and ethical considerations. And even on the technical side, there's currently a lack of clear understanding how these models work, when they fail, and what they're even capable of due to their emergent properties. So in this figure from their paper, they talk about the intrinsic biases on the left, which become integrated into the foundation model from various sources, and how when those foundation models are adapted to a specific task, that can relate in extrinsic harm in terms of the user experience, which can appear in a number of different ways. So while these models might be technologically attractive, we have to ask what are the intrinsic biases that research that we're doing might have, and what are the potential extrinsic harms as well. Morelli 2021, in an article about the ethical and political issues with AI and music creation, noted that there's an inevitable increase in the artistic surplus population and decrease in creative labor cost when these tools are introduced, due to the amount of streamlining and automation. And inherent within that is a kind of exploitative ideology. And they suggest that there needs to be some kind of ethical and epistemological turn for, in particular, music information retrieval research. But it seems to me that there could be similar exploitation happening in years to come for performing musicians due to AI NIMEs. For example, if data from performing musicians is collected and then used to improve the experience of beginner musicians at the expense of these more highly qualified musicians. In terms of research methods, for us as NIME researchers, obviously one of our favorite things to do is to put our new interfaces in front of unsuspecting study participants. And I found this paper from Shankdal 2019 interesting from this perspective, trying to understand people's mind perception and emotional responses in these scenarios. They found that more extreme responses occurred when humans and AIs were in reciprocal social roles, and where there were also anthropomorphic qualities. And I would guess that these types of experience will be present in musical scenarios, music interaction scenarios. So I think we have to consider that there might be some sort of increased risk towards the welfare of NIME study participants if they're being surprised and amazed or disappointed in such extreme ways, perhaps not now, but in the not too distant future. Oops. So hopefully I've not painted too gloomy a picture there, but I do want to end with perhaps now coming back to this idea of invention and what can we do as technologists and researchers who are developing new technologies to create a field that is building on the past and going positively into the future. So Christian Steinmetz, researcher at Queen Mary University of London, recently collected together this list of AI audio startups. And I think one thing that NIME researchers could benefit from is kind of studying this list and learning to uncover the encoded values in these companies, and starting to wonder what the potential biases and harms might be there. And hopefully this might start building up a bit of a literacy that we can then start to apply on our own research and try to understand what values we might be encoding, whether we are aware of it or not. Also, from a sort of tool designer's perspective, I've always been quite inspired by this article by the UX designer Bill Buxton, who talks about the artist spec. And in this short article, he talks about artist skills that are very different from accountants or other office workers. And he says, yeah, based on the tools used, when I walk through Disney feature animation, I can hardly tell if I'm in the accounting or character animation department. And although this article was written quite a while ago now, I think this is still largely true in the way that NIME designers and indeed AI practitioners are stuck using computers and screens and so on. And Buxton divides his own career into who he's been working for in terms of a standard UX spec, a military spec, and an artist spec. And he says that he learned that the artist spec was the hardest and most important, but if you could nail it, then everything else was easy. And after his work with artists, his research career later on was relatively simple. So perhaps a nice thought exercise then for researchers in this workshop is, what is the artist spec for the embedded AI NIME designer? Or indeed, what is the artist spec for the embedded AI NIME performer? And we can, of course, build off the tools that are already existing in our field, but I can personally recommend from my own research that looking into craft literature and materiality are really quite interesting here. You know, what is the materiality of embedded AI? How does it feel to work with, and how do we actually ideally want it to feel? And then finally, a few more suggestions in addition to the ones I've just mentioned. In the past NIMEs, we've had workshops on ideas like NIME Hub, and in this edition, there's a workshop on NIME archiving and so on. This idea of kind of pooling artifacts and resources together. And this kind of got me wondering whether there could be something equivalent in this subfield where we could share data, models, and even compute to try to alleviate this compute divide that was mentioned earlier. I think there's a lot of really interesting edge AI hardware, so to speak, that's coming into the field right now, but a lot of this is proprietary, and I think it would be a real shame if some of the best innovations in this area were confined to proprietary only solutions. And then finally, interpretability and explainability, these are two kind of sub areas of AI which I think could be really interesting for NIME researchers to explore, particularly given that we're talking about embedded systems where the thing that you have to make interpretable or make explainable is potentially a lot simpler than you know, getting a Tesla car to explain why it jumped a red light or something like that. So that comes to the end of my talk, and yeah, I just want to say thanks again. I'm really looking forward to the rest of the talks this evening. Thank you.
Thank you, Jack. That was great. Great way to get started. I think we have time for a question or two, if anyone has a question for Jack. All right, if we have no questions.
I could, yeah, I was just wondering if Jack could expand on what he thought might be the materiality of machine learning. That seems very different to what I've seen around. Yeah, would you expand on that quickly?
Yeah, thanks, Steve. So I did have a brief search about this, and I was kind of expecting this to already exist, that someone has applied ideas from materiality in the AI sphere. And particularly, I'm thinking about things like Tim Ingold's notion of the grain of a material. So I know in Andrew's lab in the past, we've thought about what is the grain of, for example, pure data versus Maximus P versus Super Collider and so on. And Tim Ingold talks about the grain of a piece of wood. You know, you can work with it in one direction, but if you work against the grain, you're going to potentially you know, not get the best out of material. So I'd be really interested to take that sort of lens and apply it to AI and embedded AI, and to ask, you know, if you reimagine this AI material as being something that you could touch with your hands, then how would it feel? And perhaps a good starting point for this would be to talk to experts in AI who've been with the technology long enough to have this sort of intimate tactile relationship, maybe. But we're inevitably going to be developing tools for creating and manipulating embedded AI. So that could also be a really interesting lens for approaching that kind of research too, I think. Yeah, thanks for the question.
All right, if anyone else has a half-formed question that they're not ready to ask, remember to note it in the Padlet or in your own notes so we can circle back to it in the discussion. And with that, thanks again to Jack. And let's move on to Rebecca.
Hi, I'm Rebecca Fiebrink, and I'm going to be talking about some unconventional considerations that arise when we think about embedded AI in the NIME space. I'll start, though, by trying to characterize the conventional story about why we might use embedded AI and what the challenges and ways to address those challenges are. So first of all, why AI? In just about any non-creative context, this answer boils down to, well, AI and especially machine learning allows us to do decision-making, prediction, and analysis just more accurately than if we were trying to build these computational systems through other means. So success in many of these contexts really boils down to, are we making accurate models? Especially, are we making models that can perform accurately in more complex real-world environments? For instance, if we've got a face tracker running on a phone, is it accurately identifying or tracking faces of lots of different types of people in different environments, even when they look different from the data in the training set? And furthermore, do these models run efficiently on embedded devices? The main mechanisms for pursuing success are deep learning, right? We can make much more accurate models. We can release pre-trained models that might be a one-size-fits-all face tracker that just runs nicely on anyone's device, or maybe releasing models that are fine-tunable by developers aiming at very specific application contexts. Of course, we've got techniques like distillation, lots of emphasis on these clever techniques to make models run more efficiently. And furthermore, people thinking about how do you make APIs for developers when we assume that they might be running these models on mobile devices or other embedded systems. Now, we can ask these same questions when it comes to NIME, and I think we'll often get slightly different answers that depart from this conventional story, and I think that can inform our research agenda in meaningful ways. So starting with why AI for NIME, or why embedded AI for NIME as well. I have two answers to this. Number one is that machine learning simply enables the creation of new types of interactive systems. Of course, in NIME, we love this. Yes, we can do more accurate sensing and gesture recognition if we're working with sensors and trying to predict what is the person doing in front of a camera, or how is somebody interacting with a device. Machine learning can allow us to do this more accurately. Beyond this, though, AI can allow us to build more complex mappings to deal effectively with dozens or hundreds of channels of sensor or other data capturing what a performer is doing. And likewise, we might be able to control dozens or hundreds of sound synthesis parameters. We can just make new types of instruments that are more complicated than we could do with programming. Of course, modern machine learning techniques allow us to synthesize new sounds. And generative techniques provide us with new types of control paradigms. For instance, if we're able to generate sound by manipulating a vector in a latent space, this allows all sorts of cool stuff, higher level ways of interacting with sound and media. For instance, here on the screen you see Google's NSynth, where we could say, hey, I want a sound that's a hybrid of these two recordings, and maybe I even get a slider to slide between the two. But it's not just about enabling new types of interactive systems. It's also about facilitating new approaches to the design of these systems. Back when I started this work in around 2008, 2009, I began exploring with my collaborators what it might feel like to build a new machine learning-based instrument interactively by creating a really small training set, capturing how I might want to move and kind of sound I might want to be generated in response to that movement, building a machine learning model that captured that relationship, playing with that model, exploring what it might do musically, and then iterating, right? Changing the training data to represent new ideas that I had about the instrument or to correct mistakes that the instrument was making. And this has, some really profound implications. First of all, if you're building instruments using this kind of process, it can often just be faster to build a prototype. It can be faster to refine a prototype by changing the training data as opposed to, say, debugging your code. One consequence of this is that you can explore more designs in the same amount of time. This approach enables you a more deeply embodied approach to the design process, which of course is super important if we're building instruments. Thinking more about modern generative machine learning techniques, of course, we can generate surprising yet potentially suitable new sounds or mappings or other types of instrument characteristics. And all of these techniques, supervised learning, generative machine learning, can potentially be more accessible to non-experts. If you can build a new instrument by providing examples of movements and sounds, or examples of sounds that you might want to play, that's something that's accessible to basically anyone with the right interface. It doesn't require programming expertise or signal processing, and so on. So what does success look like in AI for NIME, or embedded AI for NIME in particular? Do we care about accuracy? Yeah, often we do. Sometimes we really do care about accuracy in the same way as everybody else talking about embedded AI systems. If we want to build an instrument that uses a face tracker and tracks somebody's face using a camera, we probably want this to work really accurately for lots of different people, lots of faces, lots of environments. However, some instruments we might build, that's not exactly what we're trying to do. Here on screen you see Jeff Snyder's Burl instrument, where a neural network is used to take as input values from sensors under the keys of this instrument and predict as output what pitch of note to play. Here we're not trying to accurately model every single player that might potentially pick up this instrument. We might just be trying to model the intentions of the designer. And of course there's all sorts of other variations of this. We might have new instruments or interactive systems that fall in different places on this scale, from trying to accurately capture some real-world phenomena and generalize to new variants of that phenomena on one end, and on the other end, something that's really just meant to work for one person doing one thing. Efficiency and latency, of course, these are important. I'm not even going to talk about these, but what I want to emphasize as well is that there are many other things that we care about, many other things that determine whether an AI-based music system is going to be successful or useful. Things like, for instance, does it generate sound that I like to play? Is an instrument learnable, right? Is it something I can teach to somebody else? Is it comfortable to play? All sorts of things that have been written about in the NIME space for a long time now. All right, so given that success in this context is more than just about generalization, accuracy, and speed, I want to share some what I'm going to call unconventional considerations that arise when we think about how to make machine learning work well at NIME. And these are applicable to embedded AI systems in particular. So the first consideration I want to talk about is dataset size. Despite the huge focus in the rest of the machine learning community on trying to distill deep learning models and so on, I want to remind everybody that actually small data sets and really simple models might be just fine or even better for a lot of NIME applications. Some of the problems we want to model are really simple in mathematical data terms. Predicting what note to play based on where my fingers are on some sensors, yeah, that's pretty simple. I don't need thousands of examples. I might need a dozen. System creators might have a lot of control over the training data. We might not have a lot of noise or error in these examples the way we might in other contexts, for instance. As I mentioned, we might not need to generalize to widely varying contexts. Sourcing small data sets is less work, so if we're able to use a machine learning algorithm like a nearest neighbor classifier or a one hidden layer neural network, actually that's a win for us because we don't have to get as much data. And furthermore, big data sets may just not exist for many important applications. I'm going to show you a quick video clip from some work by my postdoc, Gabriele Vigliansoni. This is called RVAE. It's a variational autoencoder that generates rhythms. And here, as he mouses around the screen, you're going to hear generation from different latent vectors. Now, Gabrielle is really interested in generating rhythms that have commonalities with rhythms of African and Latin American musical cultures. And it turns out that for lots of different types of music, we're not able to get really, really giant data sets of the scale that you would need if you were going to create, say, an OpenAI jukebox style application. If we proceed with the assumption that only big data sets are useful for machine learning, we actually end up really only being able to reproduce the kinds of music that we, see in large quantities on the internet, for instance. And there's all sorts of problems with that. So RVAE, you can train it with about a dozen examples and get some really nice results. Here's some examples of the sound. Gabrielle and I have a recent paper with our colleague Phoenix Perry called A Small Data Mindset for Generative AI Creative Work, where we talk about this in more detail. So do go read it if you're interested. The second consideration I want to talk about is that we might often want to do real-time training. Again, this isn't an emphasis in more conventional embedded AI work, but whether you are training an instrument on the fly in a performance or just doing training as part of your design process, actually the speed with which this happens is really important. Interactive machine learning, of course, is the term that's used for this sort of iterative process that I've mentioned, where we might be providing data, building a model, playing with that model, and then changing the data. This is embedded in all sorts of machine learning tools used at NIME now. And this is really useful if we want someone to be able to build their own instrument or interaction from scratch. And of course, this approach often uses small data sets and simple models as well, making real-time training feasible even on really low resource hardware. The third consideration I want to call your attention to is that we might not even want to do any real-time model running. Again, this is such a research focus in a lot of the embedded AI community more broadly, but sometimes in music we can get around this by just being a little bit clever. Back to NSynth, for instance, they have a hardware version of NSynth, which you can build yourself. The sound synthesis used in NSynth is so computationally expensive, you can't even do it on real time on a really nice laptop. At least you couldn't the last time I checked. And so they actually pre-generate all the sounds. And when you're working with this device in real time, all it's doing is using a lookup table to play the sound. So yeah, we can do that sometimes in music. The fourth and final consideration I want to discuss is that user interfaces for managing machine learning data, training machine learning models, and debugging or adjusting machine learning models, these really, really matter, especially in the NIME space, right? If we're building a new instrument or building a new synthesis module, the choice of training data has a really huge impact on the model, potentially the biggest impact of any choice that you're going to make as a creator. So often, iterating on your design, saying, oh, I want this to work a little bit differently, this way or this way, that often means doing more training iteration. It might mean iterating on your choice of data, or maybe iterating on certain other machine learning choices. And often in embedded systems, as well as other types of sort of complicated hardware systems, we are collecting data using one technique in one environment. We're training in another programming language in another environment. We're using, trained models, running them in real time somewhere else. This not only slows things down, but it really impacts on our ability to think and work as designers, not to mention imposing constraints on what we can do real time in performance. So my approach is currently to say, ideally, we want to be collecting data in the context of use, performing training and iteration in that same context. And this comes in part from a project I've been working on for a few years now called InteractML. This is a collaboration with a bunch of VR researchers and VR designers who were really interested in doing Wekinator style interactive machine learning, but in VR. So you could build gestural controllers to interact with virtual environments. And for them, it was actually a huge hassle to do the training of machine learning outside VR, and then needing to put their headset on and take it off all the time in order to tweak their models. So one of the things we did in InteractML was make sure that there was an environment for doing the training and machine learning management that you could do in VR itself, so you didn't have to have that disruption. But it's not just about disruption, it's not just about efficiency, it's about the fact that the design of a user interface to allow people to build and iterate on machine learning models has huge consequences for all facets of usability, for how flexible something is, and how accessible it is to different types of people with different goals and backgrounds. I've got some screenshots here of just some different machine learning interfaces that have been used in music, and you'll be able to see really quickly these have different implications for who can use them and what they can do. So this is Wekinator here on screen. This is another tool that I've made called Sound Control, which is made for kids and teachers, and it bundles the sensors and the sound and the machine learning all in one interface, obviously hiding a lot more detail than Wekinator. This is Teachable Machine, which Google has made to try to teach anybody the basics of supervised machine learning. And this is a Jupyter Notebook. This is something I used with my students at the Creative Computing Institute a few weeks ago. Of course, each of these is going to encourage you to think about machine learning in very different ways. They're going to allow different types of experimentation. Big consequences here. So if you are building embedded AI systems, I want to encourage you to think about what do your user interfaces look like, whether those are interfaces for you, for musicians using your instruments, for developers using your toolkits, and so on. All sorts of questions here related to interfaces about how constrained or flexible the machine learning is. What can you do in real time with the body, with sound, versus what do you have to go do somewhere else in a different context? How are you encouraging people to think about and engage with machine learning or not? What expertise and training do they need? How easily can they change and refine machine learning components, and so on? Okay, so with that in conclusion, I have a few thoughts for you. First of all, machine learning and AI in NIME, they look a little bit different than they do in more conventional contexts. We shouldn't forget that. I think we can and should use embedded AI for our own reasons and in our own ways. And because of this, I think NIME has a really important role to play in challenging the dominant narratives about what AI is good for and what work is needed to make it more broadly useful. So with that, thank you very much.
Thank you, Rebecca. Another great talk. We have about 3.5 minutes. Any questions for Rebecca? Any questions from the organizers who might be holding back?
Well, given that we do have a Slack back channel, I have a question to ask all of you. I would love people to contribute in Slack or Padlet or both. If you have been developing user interfaces, again, for yourself or for other people with your embedded AI systems, I would love to hear about them. I would love for you to share them. I'd love for you to talk, share about your considerations about, especially, you know, how to not make things more difficult or more awkward in the embedded AI space, because there's so much flexibility with, you know, the interfaces we can make on laptop screens. But again, as we all know here, lots of reasons to get away from that as well. So I would, yeah, again, love to hear more about what other folks are doing.
All right, well, maybe everybody stew on that, put it into your Padlets, and we'll bring it back in the discussion. And since we're behind on time, maybe we should go on to Ezra.
Okay, great. Well, hello, everyone. And thanks for the keynotes. They're both really interesting. I'll have to return to some of those ideas a bit later. And yeah, thanks to everyone involved in organizing this workshop. It's my first time at NIME or any conference for that matter. So yeah, I'm excited to be here. And I'll be talking today about the Google Summer of Code project that I've been lucky enough to work on this summer in collaboration with the Intelligent Instruments Lab, the Beagleboard Foundation, and the Bela team. So what is this project about? So the main goal is to improve developer workflows for using AI models on Bela. So this is a pretty, kind of broad goal. It can definitely include a lot of things, and I'm hoping throughout the summer to work on, probably a bit later in the summer, work on some tutorials and documentation, and also provide some documentation around cross compilation for Bela projects, building off some of the pre-existing work. And so yeah, that's all based around this guiding question of how the development workflow for using AI models on Bela can be improved. And so for the first part of the project, I've narrowed it down to some more specific tools, mostly performance analysis tools. So benchmarking, micro benchmarking, and profiling tools. And so the goal of these tools is to provide a way of taking measurements of your model while it's running on Bela. So the simplest use case, you can see my terrible little diagram here. The simplest use case would just be to load your model onto the Bela and be able to take an end-to-end latency measurement. And then based on that, you can then compare that to your requirements and kind of go from there. But I think a key for taking these measurements is kind of once you've done that first step of taking this end-to-end latency measurement, you want to have the option to be able to go down then to a lower level, if you'd like, to then, if you don't meet your latency requirements, you want to have some pathway to be able to get some more clues about, what the bottlenecks may be and how those can be improved upon. And so after this kind of measurement and analysis step, I also want to be thinking about how we can then optimize, or how you could then optimize your model based on the findings that you found with these performance analysis tools. And so thankfully the Bela processor gives us some information here that we can use when iterating on a design. But it gives you a lot of different things that you can measure. So I mean, one example would just be cache misses. So if you know what a cache is, it's essentially just really fast memory close to the processor. And I mean, if you have done any real-time audio programming, that sometimes memory, accessing memory can be quite slow. So we want to, have most of or try to avoid going to the main memory and try to stick to using these caches that are much faster. And yeah, like I said, the processor does give some information about the number of cache misses or hits. A cache miss is if you are looking for an instruction or some data and it's not in the cache, that would be considered a cache miss, and those can pile up and add a lot of latency to your program. So being able to take these measurements could be really useful. And thankfully, you don't have to go, like poking around in the processor registers unless you want to. Linux does provide some built-in functionality for getting all this information. So part of this project will be adding some documentation or supporting code for using the Linux perf utility, which is just reading from these registers and gives you a long log of everything that's going on. And there are, of course, some visualization tools, like you can see on the right here. We just have a flame graph which shows what function calls are taking up time during your program. So something like this could be useful when you're looking to see what sort of bottlenecks you may have in a program. So for this performance analysis work, I should say that this is, and I've only really just started on this project, so it's really more of a kind of a proposal or a introduction. But yeah, so some of my goals going forward throughout the summer are evaluating some of these profiling options and how useful they may or may not be for the NIME context and for the Bela context. I have found out that this perf tool is known to be noisy on these smaller ARM cores, so it may not end up being the best option, but I will be evaluating a couple different profilers throughout the summer. And then, of course, I mean, one of the main points is to provide some good documentation and examples for how to use this sort of stuff. So you can set up your own performance analysis, Toolbench. And so another thing that I've been looking at recently are some machine learning compilers and runtimes. So the goal of this would be to simplify the runtime that you would have to have installed on the Bela. And I'm quite new to these types of compilers, but from my understanding, the goal is to translate higher level modeling languages like PyTorch or TensorFlow into slightly simpler instructions that are common between all the different front ends, and then that common language or dialect can then be optimized for different platforms. And of course, we want to be able to run these on Bela, which is fairly low level and an embedded device. So big consideration is the size and the specific requirements that Bela has. So I'll be looking more at this ERI compiler. The reason being is that it is they do have examples up already for actually some Cortex M devices, which are an even lower powered processor family. So based on those examples, I'm hoping to add support for this runtime and compiler to Bela. And the goal of all this is to be able to easily load models from, they already have front ends for PyTorch and for TensorFlow, so to be able to load models from those two tools onto the Bela with not too much work, hopefully. So I mean, some of my next steps there will be to implement a small ERI runtime that is able to take these, take the output from their compiler and run it on the Bela. And I'll be hopefully integrating this into some of Rodrigo's past work with deep learning for Bela, and comparing the benchmarks between a setup that he's already implemented that I think I'll be talking about next, and comparing that to this ERI runtime, and yeah, see what we find. And yeah, like I said, I'm just about starting this project, so I really want to hear from people who have already tried, running AI projects on Bela and see what kind of issues they ran into. And I'll hopefully be posting some updates periodically through the summer as well. Hopefully with a GitHub project this coming week that you can follow along if you'd like. And I'll post some links in the IAL Discord and the Bela forum eventually, so you can catch updates there if you'd like. And that was about it for me.
Great. Thanks a lot, Ezra. If anyone has a burning question, go ahead and ask, but I might suggest, since Rodrigo's project is so closely related, that we hear from Rodrigo next, and then we have a joint question/mini discussion session with the remaining time.
Yeah. Hello. As Ezra was mentioning, yeah, it's a closely related project what I was doing for the Bela. So this project, Deep Learning for Bela, was born out of a kind of necessity, because I was doing some PyTorch models, and I was thinking, okay, let's see if it works in Bela. But there was no, at least I couldn't find anywhere that people were running PyTorch models in Bela. And there were some colleagues we were trying also to do this. Adan and Teresa were trying to do this in PyTorch, but I thought, okay, let's try to see, maybe we can do it with another front end. And then I decided to do TensorFlow, because why not? And then, yeah, it worked, but it was not fast enough for some reason. And then I decided to do ArmN. And then I decided also to do Neural. So at the end, I was trying just to make something work. And that's why I tried all these so-called front ends, because each of them is a whole framework for training. Well, except Neural, but they are frameworks for training and deploying neural networks in embedded devices like the Bela or Raspberry Pi. And each of them has different ways of exporting their models for the embedded device and different ways of optimization and so on. So I didn't know what is the best way to do it. And kind of this deep learning for Bela project was an exploration. What is the best way to deploy a neural network model in the Bela in the most painless way possible? With that said, it was not really a painless process. It was a really painful process because, as some other colleagues mentioned already, compiling these huge frameworks for the Bela is a complicated task that actually is impossible in the Bela to compile PyTorch because it will just die. It's too big of a library to compile it on the Bela. So it is absolutely necessary to do cross-compilation. And cross-compilation comes with a lot of other things. And a lot of the project is actually the contribution of this project is to make cross-compiling environment where you can build these huge libraries and hopefully also test some aspects of it. So my setup, what I did is based on also the work of some other people in GitHub. I can send the links later, but what I did is basically I just built a Docker environment inside my computer, and there I installed all the necessary things to compile the Bela libraries, but also to compile these huge libraries like PyTorch and TensorFlow. However, with PyTorch, it was very hard because PyTorch also needs to run things while it compiles. So there was a second complex iteration of this cross-compiling setup where you have Docker inside the computer, and then you have a QEMU emulation so that you can emulate 32 bits, and then you can compile your PyTorch library. This works, and I put some precompiled binaries for TorchLib and also for TensorFlow Lite. They are already precompiled, so you can just download them and play with them. But also in those repositories, you can find the whole Docker script, how to compile both of these huge libraries. Yeah, this is a painful process, but it saves a lot of time if you want to try just to run some PyTorch model in the Bela. I did the whole build environment with CMake. I also recommend to use CMake so on because it's just such a time saver, especially when you compile these libraries, because these libraries not only have a SO file or an A file, a static file, but binary, sorry, but they have also a series of dependencies that you can only, well, you don't only can do this way, but when you make a CMake config file, you can find all what you need to just say find package, let's say libtorch, or find package TensorFlow Lite, or find package Neural, and it's all done. You don't need to do much more. So that really eases the pain of doing this process. Yeah, so that was one of the contributions of the project. The other thing that I did is a wrapper, because I saw myself repeating over and over again. Since I show you, I try all of these different frameworks. I was writing things over and over again. So I said, okay, let's do a very thin wrapper, which basically has two functions: only load the model and process the model. Yeah, so that's what I did. Also, what you can find in the previous link in Deep Learning for Bela. It's a really, really minimal wrapper. And it only works with 1D array of floats, and it outputs a 1D array of floats. There are some issues with this design because, of course, if you need the different kind of shape and types of inputs, for example, you need ints and you need a 3D array, and then as an output you need a 2D array, it will not work because the shapes, the data types of all these frameworks are completely different. So it's possible, but it's better to I think it's better to leave this with the corresponding frameworks. So my wrapper is basically just like an example how something like this could be done, but I didn't try to further design the wrapper for all possible use cases. And with this done, I also did a small benchmark. So what I did is MLP with 16,000 parameters. Yeah, 16,897 parameters. And I ran this for 1,024 samples. And then I measure from the beginning of the inference to the end in the main thread. So it's the full speed that the Bela can give me. And I did this with several configurations because the thing is each front end has different back ends. Like TensorFlow Lite, for instance, has XNN pack acceleration. It has CPU acceleration, reference acceleration. It has also custom acceleration as a backend. RT Neural also has different backend engines. Each of them it's a complex monster. There is a lot of combinations which you can follow with each of these front ends. So these are only some of the combinations. And what I found is that the TensorFlow Lite with XNN pack is the fastest of all these combinations. I cannot really say why there is, for example, this difference between the, TensorFlow Lite and XNN pack and ARM-NN, because the network is the same, and in principle they should have the same speed. But to dive into the internals of these very complex frameworks, it's not so easy. It's a challenging task. So I cannot really say why there is a difference, but yeah, as you can see, just I have some preliminary measurements to what is the fastest and what is the slowest. Yeah, so I also did examples. I will show them, but I will say first the conclusions. The translation from these Python trained models to C++ is not straightforward. It depends really on each of the front ends. As I think, I don't remember who mentioned this before, but not all operators are implemented. Like let's say you need a sign activation with ARM-NN, you cannot use sign activations because they are not implemented in C++. So you cannot use sign activations. And so on. There is like convolution, 2D convolution also cannot be used with ARM-NN, and so on. There is a lot of subtleties to what can you deploy in embedded devices. What can you export? Also, there is different pipeline optimizations because they have a lot of tricks to work in these embedded devices. So sometimes they can fuse the layers to make it faster. Sometimes they can also quantize the types. So instead of using floats, they can use ints, but then you have to quantize and dequantize things. And it depends on each front end. So what I show in these benchmarks is kind of default floats, but of course, if you want to make it faster, you can, because each of these frameworks has the ability to do this quantization and also this fusing of layers. Also, that to do general purpose inference is challenging because, like I said, you need different input and output shapes and types. Usually, it's not one does not fit all. What I also noticed while I was trying to do the examples that I will show you just now is that there is a lot of missing audio preprocessing utilities, like, for example, what you would have in libRosa for MFCCs or I don't know, some other utilities, spectrograms and so on, which, yeah, to some extent they are in Bela, in the libraries included, but I think for machine learning, you would need something like libRosa C++, but also optimized for the Bela. That means with neon optimization so that it is faster, right? And also because the Bela is so limited, you need a lot of iterations to see what it works. So this deep learning for Bela framework that I did, or not framework, but this deep learning for Bela repository kind of also can help to iterate and then see, does it work fast enough? No, iterate again. Does it work fast enough? Iterate again, iterate, and see until you reach the point where, okay, it works fast enough. And with that said, I did some examples, very simple examples. In the first example, what I did is basically I train a siren MLP. So it's just an MLP with sign activations. It's called siren. Yeah, it just learns a voice, for example. What is interesting is that because it just learns values from 0 to 1, you can send it a different curve of values from 0 to 1, and it will produce some strange sound trying to interpolate between those values. A second example I did, I took it from Armitage. It's called keyword spotting, where you input an speech signal and basically you get the features and then pass this through a neural network and it tells you what keyword is it. It has a dictionary of keywords. And the challenging part here is to implement these speech features, which are not really related to neural networks or anything. But this is the pre-processing steps that I was talking about that it is missing for the Bela library, like MFCC and so on, with intrinsic acceleration. That was the challenging part. And the last thing I did as an example is automatic equalization. So there is this, I don't know, maybe some of you know, this called IIRNet. It's based on a work by Colonel et al. And what it does is basically you send a curve of several transfer function basically, and it gives you the coefficients that you need to get that transfer function. So basically you can draw a curve and then you can have input audio and it gives you the coefficients that you would need to get that transfer function. So you can use it as an automatic equalization because it changes per block, but also you can use it a bit like a tone transfer in a way. And after several approaches, this works fine in the Bela, but it runs kind of 100%. And this is all PyTorch. Basically, it was very easy. I just trained the PyTorch model and then just deployed it in the Bela. Yeah, you can draw the curve and then you see that it tries to match per block the desired magnitude, the desired transfer function. And yeah, that's it. There can be more examples, but yeah, was just kind of something to show what can be done with this PyTorch framework. So if you have any questions.
All right, yeah, thanks Rodrigo. That's excellent. On behalf of everyone trying to do this stuff, thank you, and Ezra as well for bearing the pain. If you two have any questions for each other, or if anyone else has a question, we've got 4 or 5 minutes.
I guess I have a question. If I'm just curious if anyone's tried running some any MLIR like runtimes on the Bela. If anyone else has tried something similar to that, yeah.
This sounds like a no, but so the runtimes for these intermediate representations, are they kind of similar, just like ergonomically, to like the Onyx runtime or something like that?
Yeah, I think Onyx actually has one that's pretty similar.
But these intermediate representations are more low level than something like Onyx, right? They're like more like a series of instructions and less like a monolith graph.
It's like bytecode. Yeah.
Gotcha. What's your take on like kind of the landscape of those? You mentioned Erie, but it seems like Erie also uses MLIR, so I wasn't sure how those were related, or if is there like one that seems like it'll be the one for embedded computing and others are more like for running on GPU servers or something?
Yeah, I probably didn't explain it very well because I don't understand it very well, but MLIR is just built into the LLVM like ecosystem. Like so I think most compilers that use the LLVM backend use some sort of MLIR dialect is what they seem to be called. So Erie is also built in. They're very integrated with LLVM, and the Torch MLIR is also integrated into this Erie project. And there are a couple other examples, but I can't remember them off the top of my head.
So one question, so that means that you can only use LLVM for compiling, you cannot use GCC?
You can actually use GCC. Yeah, I'm still working on trying to get it properly compiled. They have a bunch of different outputs that Erie can output, so it can either output to the LLVM compiler, or it could just output just C code. Yeah, so there is a possibility of still using GCC.
We have a question.
Yeah, I wanted to ask a question. Like, just what do you think it is the biggest barrier into facilitating DNN deployment on Bela? Do you think it's like a particular piece of the tool chain? It's a problem of the lack of a nice user interface to upload the models? Do you think it's a problem that we can't possibly compile something in Bela? I would like to know if you have an idea of what would be the most difficult barrier.
For me, I think it's a knowledge barrier, because you need to definitely know how CMake works and how this, like what Teresa was also saying, that there is this gap between kind of intermediate knowledge and expert knowledge who know CMake and can compile these things for Docker and so on. So maybe it's just the knowledge barrier, but once you have the precompiled things, I think it makes it much easier, but still you need to know how to link stuff. And when you have some linker error, for instance, if you use a third-party library, what is this problem? I mean, when you are an artist, you don't really need to know this, but I guess at some point you are forced to learn it, because yeah, and maybe that's for me kind of the biggest obstacle.
Yeah, it's like, if I understand correctly, it's a dependency library, because there's a lot of complexity about what you explain about the Docker and all the things that hopefully you can hide from a user, right? Because you use Docker, for example, to compile libtorch, but okay, no, but we need Docker too to compile.
Yeah,
we need Docker to compile.
I use it because whenever you have a big project for Bela, right, and you have this MFCC preprocessing and so on, the bigger your project is, the more time also it takes in your Bela to compile. So anyways, I use the cross compilation. The problem also, I don't know if it would be so easy to make it for everyone, because the more general you make something, you will have always people unhappy with it and will try to tinker with it, because I need something special, you know. I don't need exactly this. I need maybe to change this and so on. So I find it's very hard to design something like this. A lot of people might get frustrated because it's so simplified. It's like a Mac, right? Or sometimes, you know, it's like you cannot tinker with it. Something like when you have a Linux. Or, I don't know. I find this might be also a really challenging thing to do, because who are you doing these tools for? If you are using only for artists, which kind of artists, right? If they are so experimental artists, then maybe you cannot do anything about that.
Yeah, I think it could be very interesting to see how can you reduce the degrees of freedom and still come up with a useful product that can hide a lot of this complexity to an end user. Yeah. Great.
Okay.
Great job, honestly. Thank you.
Thanks for the questions, and thanks again to Rodrigo and Ezra. We've got some more questions in the chat, but I think we'll save those for the discussion later because we're going over time. And we've got one more talk before our break. So I'd like to invite Tom.
Hi, can you all hear me?
Yes.
Great. Okay, I'm going to share my screen here, put up a little presentation. I think a lot of the things that you were just talking about are going to be really relevant to what I'm about to talk about, especially about the need to get good latency for real-time audio applications, which is obviously a crucial part of making instruments with machine learning, without needing to necessarily optimize the model or maybe like break down things to the point that it's useless for an artist. So I think we can probably help with that quite a bit. So I'm one of the co-founders of the startup Tensil.ai, and what we actually make are custom hardware for machine learning. And this is how we solve this problem of getting you real-time latencies that are useful for making musical instruments and not putting an onerous burden on the artist to hack away at their model until it's so tiny that it can't even do anything. So I think maybe just before I start, you may or may not know what an FPGA is, but I think that's going to be a crucial piece of vocabulary because that's the easiest way for people in especially audio applications to actually deploy custom hardware. So an FPGA is a field programmable gate array, and it's essentially like halfway between a custom chip and a generic CPU, let's say. So one of the previous talks was, the previous talks were talking about using ML models on ARM CPUs, and those are generic pieces of compute hardware. They can run any program, but they're not necessarily optimized for any particular workload. And a custom chip, as in something you would go to a foundry and get taped out, would be a very, very optimized thing, but is maybe a little expensive. And so an FPGA is kind of halfway in between. So I definitely encourage, if you haven't already, if you don't know anything about it, I really encourage you, especially people trying to make real-time audio applications, to check out FPGAs in general, because I think it'll probably be very useful to you. And then within that space, I think we have something interesting to share with you about how to actually deploy ML on those. Okay, so that's what I'm talking about today. So just trying to make it a little bit relevant to NIME, because you can really deploy any kind of machine learning on Tensil, and we want to make it as easy as possible for anyone using machine learning models to get them running on their own custom accelerator. So literally 2 commands here, and you have a custom piece of hardware, a custom accelerator that can run your ML model and is optimized for it. So the top command there is going to be generating a hardware description, which you then program into an FPGA. And the second piece there is actually compiling your machine learning model for that accelerator. Okay, so I know that this is probably, this is maybe going to be like too technical for some people and not technical enough for others, so I apologize, and please ask questions if things aren't clear. But I really want to emphasize that it's super easy to do this, and I do encourage you to check out the tutorials we have. We actually just put one out about an audio application, which I'll show you at the end of this talk. So that might be a really good place for people in the NIME world to start trying out ML with FPGAs. So like I said, we have an RTL generator, we can compile your model. We also have runtimes and drivers. So again, the previous talks were exploring how to use the runtimes that exist. We actually provide a real-time runtime that's suitable for embedded applications. So it's going to be really suitable for making an instrument with, because you'll have deterministic latency, essentially. The other cool thing about Tensil is that it's open source and it's free, so anyone can use it. We are a company, so there is a business model on top of this, which is based on basically offering enterprise support. But for people in the NIME world, I think the free and open source version of this is going to be more than enough. And so I think it's hopefully going to be useful for you all to play around with. So I'm going to explain a little bit about, a bit more of the nitty gritty here. If this isn't your thing, maybe tune out for a second while I cover that, and then I'll explain at the end about the audio application that I think might be interesting. Yeah, I think for the NIME world, like the prototyping stage here is really what you're all about, and we really make it easy to do that piece of things. So you don't need to modify your model, you don't need to optimize it or hack away at a machine learning model to get it running with Tensil. Unlike with other embedded applications where you will typically need to, as the previous talks were saying, do a lot of work just to get it even running on an embedded platform. We're taking away all that burden by offering custom hardware that actually does that work for you, essentially. And then if you wanted to do this and make 100,000 of the instrument that you're designing, we could also help with that, but I think that's probably like less relevant. So right now what we can support any neural network up to a convolutional neural network. Generally, we're targeting what we're calling edge applications, which really just means embedded. And then, the third big reason why you should use Tensil is you don't want to spend the time changing your model before you've even figured out if you're happy with, the instrument you're designing. So I think that's going to be really useful and crucial for NIME practitioners. And if you want to learn more about, what we can do right now, what the limitations are, what the future plans are, we have a Discord channel, which there's a link to in this presentation at the end. So, please come and talk to us about that if there's a specific thing you're interested in. It's very, very easy to pull down our tools. You just go and pull down the Docker container and jump into the shell there, and then you'll have everything you need to start generating accelerators and compiling machine learning models for them. So it's all self-contained and really nice there. This is what you get when you actually generate an accelerator. So what you're seeing here down the bottom, a bunch of Verilog files. Verilog is a hardware description language. And you can basically think of it as a list of logic gates and connections between modules and stuff like that. So that's the hardware description. You don't really need to understand how that works. You can parameterize it by messing around with the architecture file that is the input to this step. And so if you want more juice, you want more power, you want a more powerful accelerator, you can actually increase the parameters basically. Or if you want it to be more efficient and fit on a small FPGA, you can lower them and kind of tune things to whatever suits you. Once you have the accelerator generated, you flash it onto an FPGA. We have tutorials and scripts that basically do all this for you. But if you want to know the details of how this works, it's all on our website, and I'll point you to that at the end. But basically, this is get it on FPGA and then compile a machine learning model to that accelerator. So what you're seeing, the output here is actually the compiled artifacts down at the bottom there, and then a few stats that the compiler is going to tell you about things like how long is this model going to take to run, how well is it utilizing the available resources on the accelerator, that sort of stuff. So again, this can help guide you in deciding, okay, do I need more accelerator? Do I need less? Should I make changes to my model? Whatever. And then when it comes time to run things, we have multiple different runtimes here. I'm showing you the Python one. It's probably the easiest one to get started with for prototyping, but we also have an embedded C driver and runtime, which is going to be really good for real-time applications as well. And this is quite literally, this is the code. This is not, I'm not eliding anything here. This is all you need to get Tensil running. So it's very, very easy and fast, which I hope is very helpful to people prototyping new applications. This is a diagram of the accelerator architecture, just to give you a sense of what's going on. If you don't know much about computer hardware, don't worry too much about this, but if you are interested, at the heart of Tensil is really a systolic array, which is really good at accelerating matrix multipliers. And matrix multipliers are at the heart of machine learning models. So that's really what all of this is built around, and that is, that's where we're getting this great performance and these deterministic latencies that can be useful in real time. There's also an instruction set here, and I think I'll leave this to, if you want to explore this, all this info is on our website as well. So I'll leave it to you to look it up if this is kind of your thing. But there's an instruction set that you can learn about, and this describes what the accelerator can actually do, and the compiler is going to take the machine learning model and target this instruction set. And this is kind of what the compiler does, just to give you a very high-level overview. It reads in either, and I should actually point this out, there's two front-end formats that we can accept. So one is Onyx, which I believe someone just mentioned before. We can also read in TensorFlow and TensorFlow Lite. So you have a variety of options there. We generally recommend Onyx. It's a little cleaner as a format, but TensorFlow also works great. And then the compiler is going to take that model file and compile it down to a program that runs on the accelerator. And then here are some benchmarks this is an image recognition model, so maybe not as relevant for you guys, but just to give you a sense, this is actually a relatively, it's like a relatively large model. So you can imagine that most audio models are probably going to be a little smaller than this, so the performance is going to be quite good. And I think this should be more than enough for a very wide range of new music kind of applications. And this is a convolutional model as well. So I think that's going to be really useful. Convolutional models in audio seem to be doing quite well. Okay, so here's the links at the end. If you want to talk to us about what you can use Tensil for, you're just curious, or you have a specific use case in mind, whatever, please come talk to us on Discord. We also have a variety of other places. And then the last thing I would like to share with you is just our audio tutorial. So this is about building a speech-controlled robot with Tensil and an RDA7 FPGA. So it's a speech application, not a music application. Unfortunately, we're a small team, so we don't have a music-specific application built yet. But I think this will be a really good starting point for anyone interested in doing music-related things with ML on FPGAs. And yeah, basically this application shows, training this robot to respond to some keywords, and then it's going to act on those keywords. So I think there's a lot that you could probably do with that, and this will show you how to get things like, FFTs running in hardware on an FPGA as well. So that's actually going to also, accelerate a lot of the real-time audio processing you need to do. Cool. I think I'll stop there. Thanks very much for having us here, and I hope this. I hope that Tensil can be useful to you as we prototype new instruments, and I'd love to, stay in touch with this community and hear what kind of things you develop.
All right, thanks a lot, Tom. Really exciting stuff. We have
absolutely.
a question. We have a question in the chat already from Andrea, asking about the cost of the target FPGA boards. Just ballpark, like how affordable are those?
Yeah. So this board here, RDA7, is about $100. Some of the other ones we have here, the Ultra 96 is about $300. The Pink C1 is about $150, $200. So these are all relatively affordable, I would say. So hopefully good for academic kind of environments where I know funding is always an issue. Yeah, all our tutorials are based on very affordable development boards. You can actually get them cheaper if you buy in bulk. That's probably not a use case that many people in this community would be looking at, but there is also that. So they can get maybe even like, down to $20 to $50 range if you're buying like thousands of them. But yeah, anyway. Do we have another question there?
Question from Domenico.
Yes, I have a question. Do you happen to know the latency that gets introduced by the AXI interface? Because like these FPGAs usually present a very high throughput, which is great. Yeah. But maybe for musical applications, what we need very short latency, and usually the interfaces are a little bit difficult with that, as far as I know.
Yeah. So
the AXI interface is the controllers, the drive.
Yeah, the AXI interface is, we're talking microseconds. So it's not. I think it depends on which board you're using, to be honest. Like these boards all have different FPGAs on them with different process nodes that we use to manufacture them. So that's really what's going to drive the latency. But we are talking like 1 to 100 microseconds is typical. So probably the memory latency there is not going to be a barrier to doing real-time processing. And these numbers here, show even on a RDA7, which is a very low-powered FPGA. We're talking like, very, very small and suitable for low-power applications. Even there, an image recognition convolutional model with 20 layers is getting, 20 milliseconds of latency. So you can run this, 40 times a second. Or I think most audio models tend to be smaller than this that I've seen. So probably the latency you're going to be able to get will be, maybe in the 5 or 10 millisecond range, even for a relatively like a substantial model. And yeah, so does that give you a sense of the kind of numbers we're talking here?
Okay, great. Yes, thank you. And are you running do you have an MLP operator implementation, like an MLP primitive operation, meaning like a non-convolutional matrix multiplication operation?
Yeah,
because like, for
do.
example, I know that in some architectures, the matrix multiplication, the basic one, is run on the CPU, whereas the convolutional multiplication is done on the FPGA.
Yeah, we implement the matrix multiply.
Accelerator.
Yeah, this is a great question. We implement the matrix multiply on the systolic array as well. So it has been a basic MLP layer is also going to get accelerated. Yeah.
Nice, very nice. Okay, great. Thank you.
Yeah, for sure. Was there one more question? I thought I saw someone had their hand up.
Yeah, I've got a question.
Yeah, please.
I was just wondering if you tested this with any of the open source tool chains like IceStorm or Simberflow.
We're actually working on a Lattice version of this right now. So all these are Xilinx FPGAs. The Lattice one is going to be basically the same. So we're actually right now, Tensil does work on Lattice, but we're kind of tweaking things a little bit just to account for like some subtle differences between Xilinx and Lattice. So once that's completely done, so we do basically have a, you could take IceStorm, for example, right now and use Tensil to generate the Verilog blob that you then run through the IceStorm tool to deploy on an IceStorm FPGA. So you can absolutely do that right now, and that works. And then we're going to be releasing a couple of optimizations that make that like even better quite soon. So we haven't done a whole lot of that ourselves, but that's definitely a thing that like people in the community are doing. So I encourage you to check it out and give it a try if you're interested.
Very nice, great to hear. Thanks.
Yeah.
All right, thanks again, Tom. I think any further questions we should hold until the end or for offline on the Tensil Discord or what have you. And we've got a short break scheduled in now. So I suggest we just take until the hour, if that sounds good to everyone. Cool, I'm getting nodding and thumbs up. So I'll see you all back here on the hour, and then we have 2 more presentations, which I believe are in more of a project-y vein, less of a low-level tech vein. And then we have the remaining time for discussion. Thanks again to everyone who's presented so far. Hey, everybody. Welcome back if you are back. If Andrea wants to go ahead and get ready to go, I think we should try to keep the schedule as much as possible so we have time for discussion.
I'm going to present, as Steve said, I'm going to present a little project that involves not necessarily or not yet embedded AI, but definitely real-time AI in a musical instruments sort of scenario. So very relevant to this crowd, and it's real-time deep neural network inference in Max MSP, and the framework of choice for this is TorchScript with all warts and all. So before I even start, I'm really glad to say that what I'm going to present is has been largely made obsolete by the past 3 talks, and I'm really happy to say that to say this. There's so many better solutions to the problems that I'm going to present that I'm really eager to try. But basically, the spirit of this presentation is the "Am I doing this right?" sort of exposition, or in other words, I'm going to present a DSP engineer's first foray into real-time AI, because I am very much, in the way I think, in the way I frame my problems, a DSP engineer, and not necessarily yet an AI researcher. So I'm going to explain to you the use case, my use case for real-time inference, and then the choices that I had to make around data features and architecture to make this happen, the framework that I chose, and the way that the signal flow works, the programming model that I'm using, and then the result that I got from an initial implementation and some early tests. So my case for performing real-time inference with a deep neural network, well, in general, I've always been curious about this high-level question. So I want to have a neural network that performs like a DSP block, so something that you can put into a max, a max environment or a VST. And my specific application is an augmented guitar that processes body hits, such as the ones that you find in percussive fingerstyle, through a physical model. And I want different hit types, for example, a hit with the wrist or a hit with the fingers, to produce different sounds, controlling a set of continuous parameters on the physical model whose interface you see there. So, for example, like a certain hit would produce a sound that is more that is closer to a metal plate rather than, for example, a glass membrane. And I'm using an off-the-shelf physical model that was developed by Prism Laboratories in Marseille. So, if I want to be a bit of a philosopher with this, I'd say that my problem is that we need a system that performs inference more quickly than our brain performs inference on the same problem. And if I want to be provocative about what we've discussed, I would say that the constraints around the model in a real-time environment are actually even scarier than the issues with tool chains or even computing power. So what are the practical limitations that we have in running a neural network in such a strict real-time environment? So my approach with this is that I wanted to know the constraint of my target system and build the data set, the architecture, and my training routine around those constraints. So I've basically focused my choices around 4 decisions or constraints. The first one is, well, is your problem, is your instrument an instrument that reacts to events? So do you need to do event-based processing, or do you want to do continuous processing like a phase vocoder, which would be the application, for example, for, I don't know, timbre transfer? And then can you focus, can you really commit to a latency requirement? Do you really need to abide by the golden rule of the 10 millisecond for the absolute worst possible case for immediate immediate reaction to a percussion instrument? Or do you have a little bit of slack? Perhaps if you're doing something about the timbre, you can let the attack through and then buy yourselves some time to process only the tail of a sound. And then the other, the other constraint that you cannot escape is there is no future. You can't do bidirectional RNN, and also you cannot absorb a whole event before committed to a decision about it. If you're doing, for example, a real-time classifier, and that also made me think. And this is more like a suggestion than a constraint. But perhaps we should think outside modern MIR. So instead of looking at massive, massive VGG-ish networks, we can perhaps take a step back into the literature and dust off things like hidden Markov models and dynamic time warping, which don't really appear very much anymore in modern MIR literature. So I chose TorchScript. Why? Well, most MIR literature has PyTorch sources, so I knew that I could, ideally deploy those models straight to a TorchScript implementation. So a more sensible choice for this, especially after what we just said, could be TensorFlow or TensorFlow Lite. But the thing is, PyTorch also offers 2 C++ deployment frameworks. So you have libtorch if you want to re-implement and fight your model in C++, and then you fine-tune or deploy it in C++. And it even supports autograd, so it supports training on an edge case scenario, on an edge scenario. Or even simpler is TorchScript. So it's a just-in-time compiler that uses both the architecture and the weights from a Python script. So you can define the architecture and train your model in Python, and then just flush some bytecode onto a C++ black box, which is what I chose to do. So let's take TorchScript for a spin. The programming and threading model that I decided to use is also the picture is wrong because I made a mistake in making the diagram. But basically, you have an audio rate thread that just continuously stores the samples coming from a max external into a circular buffer, and then you have an event detector. And when that event detector detects that something's going on, then it triggers in another thread neural network processing. which then takes its sweet time and then returns a stored value, which is passed back to the audio rate thread and to the outputs of the max MSP object. The implementation of this wasn't particularly trivial, but it wasn't it wasn't a nightmare either. I'm linking some. I can post these links if any of you is curious about doing something similar. So Torch script's official guide to just compiling PyTorch is really useful. But also if you're not using a Mac, compiling libtorch for Visual Studio is a separate tutorial that you need to follow, and then for Max MSP externals, their own SDK is really good, and it's got lots of examples that you can steal from. And then if you want basically the threading model that I've implemented here, there's an answer on Stack Overflow that has got it's a producer and consumer sort of model, so it's quite trivial, and it's all based on standard thread coming from C++11. So I've implemented all of this, and then in order to test if what I was doing made any sense and it had any chance to run in a real world environment. So I've validated the C++ model against a test set that I was performing inference with on Python, and I found, much to my dismay, that there's a rounding error of around 1% in the likelihood calculation. So the PyTorch model isn't exactly the same as the as what runs in the just-in-time compiler. The latency tests are slightly more encouraging. So I got 20 millisecond if I keep my network exactly as it is, but if I remove one convolutional layer, I get down to a 3 millisecond for the inference on one window. So that's actually a useful figure. And so I'm quite happy to go ahead with that. What are the downsides? Well, firstly, there's no reason why the Python model and the C++ model aren't bit perfect accurate, and I don't understand why. But the other thing is there's actually a big variance in the latency. The average figures are actually quite okay, but especially in the first few runs, you actually have latency latency spikes that go all the way to 100 milliseconds, and that's of course absolutely not acceptable in a real-time scenario. And related to this, libtorch has quite an obscure API. Like you don't know how much memory is dynamically allocated, how many threads are running in the background, and what sort of priority those threads have. And I think this is related to the fact that you have really big latency spikes because you never know what the operating system is doing with that model. And I'm really hoping that a different framework can help there. So I wonder if this is a problem that is just related to Torch script, so just to the just-in-time compiler, or it's actually a feature of libtorch. So I don't know if I should re-implement the architecture in libtorch and retest, or just switch to something else. Based on what other people have told me in this workshop, I probably should switch to a far better framework. But basically, I just wanted to share my experience with just getting my hands burnt with one of the first real-time DNN implementation in Max. And thank you. If you've got any questions, and especially any suggestions, I'd like to hear from you.
All right, thanks a lot. It's really great. I think it's really helpful to have such a nice concrete example of trying to actually do something with this stuff. It's really clarifying as to what Rodrigo and Ezra and Tensil are attempting to do. If anyone has a burning question, I see Domenico's hand is up. Actually, we could take that.
Yeah. Can you hear me now?
Yes.
Yeah.
Okay, there was a problem with the microphone before. Yeah, just I don't know if it's a question, but I was jumping in my chair during the presentation because we had the same exact problems with libtorch, TorchScript, and everything. crazy different latencies and latencies that are completely changing before the first execution for a number of executions that are going all over the place and then they stabilize. So yeah, that is common, and only with that kind of.
Okay, it's a feature, not a bug.
Yeah, it's a feature. And then in the end, what kind of percussive hits were you classifying? How many or what? It's really interesting.
Well, at the moment, I'm doing something minimal. So based on some studies that I did in the past, the main the two main gestures that you can do is really wrist hit against everything else. And so it would be really nice to, for example, have something that sounds a bit more like a kick or a bass drum, or like something deeper when you're using the wrist. And I think everything else can be something a little bit. I'm gonna say snare-like, but it's a very loose definition. But what I'm determined to do is break away from the idea of hard classification and just use those categories as extremes and as a sort of points to bias the network to. But I'd like the network to also appreciate the individual differences, like within one category of hits and also across the categories.
Yeah. Thank you very much.
Thanks again, Andrea. We've got to hear from Franco, and then we have the remaining time for discussion. So Franco, if you want to go ahead.
Okay, just wanted to say before starting that this has been great, a great workshop, and it's been great to hear all the projects that the presenters have been doing and the keynotes. And this is the last last presentation. Work in progress also project where I combine neural audio synthesis and also like an implementation in an embedded device. So I'm a PhD student at the Augmented Instrument Lab in Queen Mary University of London. My name is Franco Caspe, and I'm conducting this project with my supervisors, Andrew McPherson and Mark Sander. So the project is called Real-Time FM Tone Transfer with Bela. And let's start with a short recap. So tone transfer is a process of style transfer or timbre transfer, originally presented by Google Magenta Labs, where they use neural networks to transfer from an audio source without altering the content of what is being played. So pretty much what we have here is like we employ a neural audio synthesis algorithm, that's the NAS algorithm, that feature a neural network that learns to generate audio from a particular dataset. And tone transfer is a type of playable neural audio synthesis algorithm and requires an audio input or features from an audio input to convert timbre. And a problem we notice is that usually neural audio synthesis algorithms act as black boxes, and it's very difficult for a user to manipulate the synthesis process that is taking place in the algorithm. For example, in case we want to search for new timbre. So this means that usually these neural audio synthesis algorithms, when we want to generate different sound, we need to retrain them. And that brings us a lot of different problems, right? So our motivations for this project are pretty much twofold. First, we would like to implement an algorithm that we can control in real time with a musical instrument. But then we would like to intervene the synthesis process generation to be able to manipulate the timbre while it is being produced. So we have an intimate control with latency
latency, and also with the synthesis process. We notice that the neural audio synthesis algorithms present a hierarchical audio generation structure, as shown in the figure. And we have a high level stage that usually operates at a slow frame rate and a sample level stage that is much faster. So we want to break into the high level temporal space and be able to modify this representation following a particular premise that the user may want to do. So this idea allows us to define some requirements for our implementation. We need stable and short latency. We need an execution that needs to be guaranteed by a real-time computing platform, so we decide to use Bela. We want the neural audio synthesis algorithm to be small enough so it can run in a single real-time thread. And we would like also a compact set of sound design parameters, so the process is easy to be intervened. We're going to take now then inspiration in other successful neural audio synthesis algorithm, that is DDSP. We talked about this, or we heard about this in the previous session of this workshop. And I decided to implement that neural audio synthesis architecture that actually controls DSP block like DDSP, but in this case, we control a frequency modulation synthesis block. So FM synthesis, or frequency modulation synthesis, generates audio, different timbre, by modulating in frequency a group of oscillators following a particular routing or interconnection between these oscillators. So it naturally yields a compact set of parameters, as shown in the picture. For instance, we can generate complex and distinct spectra with only 2 oscillators by controlling the amplitude and frequency of each one of the oscillators, or that are also called operators here in the figure. So we can add more oscillators for more timbre complexity and more degrees of freedom. So knowing our architecture, the requirements, and the DSP block or the FM structure that we're going to use, we can define our architecture. In this case, is similar to DSP again. It works by extracting from an original window of audio. We extract the fundamental frequency and the root mean square of the power of the signal, the RMS power. And we require a monophonic pitch audio signal. And these features are fed to an RNN, to a recurrent neural network, which is an actual AI algorithm that maps sequences, input sequences to output sequences. In this case, the output sequence are the oscillator envelopes of a FM synthesizer. So, and of course, the FM synth in the style of DDSP is tuned at the detected frequency of the input audio. So again, during inference, the RNN acts as a sequence mapper from the audio features to the FM parameters. And in this case, the FM has 6 oscillators. Therefore, the architecture features a very compact control parameter space. This allows us to speculate that maybe in principle, we can use a very small DNN to control this space, because the space is very small, right? We only need to control very few parameters for this synthesizer in order to produce very complex timbre. So we train our architecture in a similar fashion to DDSP, and we deploy this pipeline in Bela, which is shown in the left here. So in Bela, we fetch a small audio frame, actually a 4 millisecond input audio frame, and we synthesize a new audio from it in less than 4 milliseconds. And this allows us to define a round trip latency of 8 milliseconds in Bela. So we can guarantee that the whole process gets executed in 8 milliseconds. We also run the Bela audio codec at 16 kilohertz in this case, in order to deal with less amount of data, because we receive less data, so it's faster, the computation of, for example, the feature extraction. And we also are synthesizing at 16 kilohertz, although it is not very necessary because the FM synthesis is very small. This the table on the right shows the amount of time that the different computing tasks takes for our pipeline, which is about 3 milliseconds in this case. Around time to execute the whole pipeline, or sorry, to produce an algorithm that has a round trip latency of 8 milliseconds, which should be good enough, right, for an intimate control of this architecture. So I connected the Bela input to my electric guitar, and now let's try to wake you all up with this very short demo. So I would like to share first some remarks about this. We see that the pitch tracking may miss some of the notes depending on the way they are played. I think that's because like the guitar has a monophonic output, and it would be way better if we have like this like polyphonic output for the guitar, one for each string, for example. But yes, like the timing is not that good sometimes for short notes, because the algorithm, of course, introduces a latency, and this latency, although it's very small, like milliseconds, should guarantee like an intimate control. Still, it's a little bit problematic for short notes. Yeah, I also detected something very interesting that happens sometimes when playing the instrument. For example, the pitch tracker may lock into two different frequencies if you play slightly two strings at the same time. And this is actually some kind of like meta FM modulation that happens from the actual input. So it generates a growling sound that is very interesting. And another interesting remark is that, for example, due to the data that I used to train this neural network originally, the network learned an inverse amplitude gain with respect to the RMS input, meaning that when the output volume increases in Bela as the input energy of the guitar decreases. So it's very interesting. It's kind of like an inverse mapping there that it learned. Since these networks are very small, we can really expect tracing from the output. So, for example, although I trained this network with a collection of trumpet sounds, it really doesn't sound like trumpet. But the important thing is that this algorithm represents the possibility of deploying complex mapping strategies to control a synthesizer from continuous audio in real time. So for next steps on this project, I will work on the potential affordances that the FM parameterization can yield. Actually, I want to manipulate not only the FM controls, into this user intervention scheme that I showed before, but also there has to be a way of manipulating the envelope generation that they're in the ways of the network. So yes, and honestly, if like we require to know a little bit of FM synthesis in order to manipulate this the generation, but we could always try and generate some meta controls, group these controls, FM controls together to generate easier to understand or easier to manipulate controls. So that's also another possibility for this project. So I would like to acknowledge my colleague Rodrigo now, who did an excellent job in making these deep learning tools available for the Bela platform. I use LibTorch. For example, he's a LibTorch build for this project. So honestly, this project it could be impossible to do this project without these tools. So yes, great job, Rodrigo. Yes, I'm happy to take some questions now. I will release the source code soon for this application after I polish a couple of things more. And feel free to follow me on Twitter or like to contact me directly. And thank you.
All right, thanks a lot, Franco. Really good stuff. Does anyone have a burning specific question, or we can just segue into the general discussion as well? I'm curious, when you say you trained on trumpet and then you were using it for guitar, does that mean you trained on a data set of trumpet sounds to estimate the FM parameters that reproduce the trumpet sound?
Exactly.
And then
yes.
You just use that model with a guitar, and you noted that it kind of get a guitar synthy sound. It doesn't really sound like a trumpet, but I guess.
Yes, actually, this video that I made is that model trained on trumpet, but with some modifications. So the model, for example, instead of working as an RNN, it works as a stateless model, because I found out that actually the sound is way more interesting than like a very small model trying to reproduce the trumpet sound very loudly. So this opens opens up the possibility of studying these very small networks for mapping, or for mapping envelopes in synthesizers. We really don't necessarily need to stick to the sound they were originally trained with. So this is something that I will explore next.
Oh, I think I actually understand what my actual question is. Is the tone transfer method, does it take just the amplitude and frequency curves, just those two as an input, and then it uses that to reconstruct? Okay.
Yes, yes.
So like the guitar, like the curves you would get out of the guitar might be a bit out of domain, but you'd expect it to do some kind of timbre transfer to trumpet when it's a trumpet-based model.
Yes, I'm actually not expecting to work as a like a trumpet, because I actually modify the network. I train the network to like generate trumpet sounds, but then I modify the way in which it is executed. So I'm actually not expecting it to generate trumpet sounds, because it's such a small network. Like we were saying before, in LibTorch is not very well optimized to run in Bela, for example. So you really need to deploy very small models. These models are actually not very well sounding. But anyways, they are very interesting in terms of the mapping that they build inside. So if you can manipulate this mapping, and especially you can manipulate the let's call it intermediate representation in terms of FM parameters, which are actually interpretable by a user. So then you get a very wide tonal range from a model that was trained on trumpet, human voice, whatever. I'm suspecting it actually doesn't matter that much on the type of data it was trained, as long as you can modify it and you have a good set of understandable parameters to modify.
Gotcha. All right, well, thanks again, Franco. Thanks to everyone. We have about 25 minutes or 20 minutes or so for general discussion. If everyone wants to take a moment to glance at your Padlets or your notes, or if anyone has a question for any of the speakers ready to go.
Jack, you just reposted the question, which I was going to highlight. Do you want to expand on that?
Yeah, I guess as software developers, probably some of us are familiar with the phrase that premature optimization is the root of all evil. I think the full quote actually says that 97% of the time it's the root of all evil. So maybe we're in the 3% where it's actually the most appropriate thing we could be doing right now, because we actually want to be able to interact with these things, you know, in a responsive enough way. But I think in any optimization process that's involving artistic applications, there's potentially a problem of, you know, fixating on a problem at the expense of exploring some odd, eccentric, creative options that if you put them in front of an artist, they might say, "Hey, what was that? That's amazing." So I wonder if, you know, how far are we away from that point? And you know, for those who gave the tech talks today or this morning, how far away do you think we are from this point of wanting to get artists in the room with some demos and just making sure we don't optimize out the interesting stuff? Or if you think we're just so like very far away from that point, then you know, what do you think that point might be?
I'm going to try and give you a stab in the dark answer. From my experience and from what I could read, the problem with I usually make this as a case for not using classifiers or not using hard classifiers. Like when a conventional machine learning agent falls apart, usually it falls apart really, really hard. And I've observed how in music you tend to like at least a sort of local organic response. So when you move around, when you move around some imprecision, at least you don't want something to completely fall apart. So I think some, let's call it optimization, if you want to call it that way. But I mean, at least we need to get to the point where we can produce something that is as organic as what we can expect from the instruments that we're used to. I mean, that would be a massive milestone, I think, for us as the AI community in NIME. And we're definitely not there yet, because we barely have some network architectures that can give us that results. Latent spaces may be going in the right direction, so the idea of using VAEs may be going in that direction, but we are so those latent spaces are so difficult to interpret that. So I think we are at the stage before that. This is why I also said in my presentation, like the biggest challenge that we have is not the it's not even the computational power, is that we don't have the architectures that we can use yet.
As long as we're unmuted over here. I think there's a lot of truth to that, but then I think also there are ways in which a network that falls apart can be an interesting creative resource and can even be designed for. And also, I think a lot of traditional instruments and experimental instruments alike have quite abrupt transitions between one set of behaviors and another, but oftentimes that edge is extremely interesting. So, here I come back to one of my favorite phrases this is from Tom Mudd, the edge-like interaction, where you kind of explore regions between stability and instability. I think that a neural net could potentially give you that. The question is, do you know where the edge is, and is the edge in some way predictable so that you can walk up to it? I mean, it's the difference between walking up to a cliff and looking over the edge and walking up to something where you know that the ground might crumble out from under you at any time, so you can't get anywhere near it because, do so at your own risk.
On that, how quick makes me think about the hardware developments. How fast, you guys know better than me, how fast is hardware like to develop around you to kind of pull that edge back a bit more? Or make it clearer? Does that make sense as a question?
Yeah, I can talk a little bit about that, but also I was thinking maybe when we try and optimize to get the best latency and everything, we may leave behind some interesting stuff, right? But also as makers, I think that it's pushing us. Like it's pushing some creative constraints, and this also can help us to realize and to find workarounds and to find very interesting solutions that still comply with the requirements that we want. So I really don't think that by trying to optimize we are leaving things behind. I think both approaches can be equally as creative as interesting. For example, this is what I believe. I would never have thought about like modifying, for example, like the weights of a neural network just because the results are not that interesting. But I'm finding that can yield to very, very interesting applications. Yeah. And about the speed, if you were saying about the speed related to the latency or the speed of the devices that we're using to compute the neural networks.
I was about the speed. I was about devices, because I was thinking how my practice years ago, I built one of the first solid state surround sound locative systems, hardware systems, which took a lot of effort, a lot of hardware, and took it right to the main thing to the edge. Then a few years later, I can do it on something a tenth of the size. So what I had was my edge disappeared around me as hardware caught up. So for a while I accepted the limitations, knowing that eventually the hardware is going to allow me to do what I'm seeking. I'll just wondering where we are in the equivalent journey in the systems that you're talking about.
Yeah, I understand. So, and I think in that sense, it's also interesting to try and optimize things, because we can get a glimpse of what's coming up, right? So I think that's also interesting. Like, we should embrace latency, but we should also try to optimize some things and see how far we can push this technology, and also to be able to take a glimpse of how are we going to use the faster devices that are coming up. My take on it.
Yeah, I think that thought, Steve, is very interesting. Like, why don't we just wait like 5 years, and then we maybe will have like super cool GPUs. I don't know, we won't have to maybe even compile things from source. We will just have like, I don't know, we can build like, or I don't know. Well, I don't think we'll ever get rid of compiling things from source, I guess. But yeah, why don't we just wait? And I think that while this is of course an option, not for us that we're doing our PhD now and we cannot just wait. I think that and this I think relates a bit maybe to Rebecca's question. Like, I just think it's interesting to think, what if AI doesn't have to be that accurate or that specific? And like, okay, we have like this in NIME, we have like those requirements, like, okay, we have these latency ideas. And then there's a question that Jack was saying, like, do we need to stay in those margins when there's maybe new things that we can do, even if not respecting those margins? But I think, yeah, I've been thinking a lot about ambiguity and like how these notions can be explored by using AI in instruments, and how these notions totally diverge from the idea of accuracy and yeah, these words that Jack was mentioning as well. It's nice how it all comes together. But I think that embedded systems really like make you think about these things, like yeah, I don't need a transformer to write an essay on existence for me in an embedded system. I just want something that is able to interpret my gesture and make music with it, and make it in a cool way, in an interesting way. Do I really need like a super large network for this, or can I play with my limits? And this even reminds me of like all of this idea of affordances and constraints that I mean, yeah, we all know, yeah, Thor's paper and these ideas of, yeah, how, yeah, I think you can apply that for so many things. Just having those limits, it really like brings you to think about, yeah, what can we do? There's a lot of also in using super large computing system, or this like techno-positivist notion of like, we're doing it because we can. And it's like, here in this domain, I feel that we're trying to do it because we can't actually. So we're just trying to do things that we don't think we can do it. So it is, I think it's very different ways of thinking that are very cool, creative, and in this domain that it's like has these sometimes ambiguous notions like of what's good, what's bad, and yeah, good instrument, bad instrument, or yeah, I think that's what makes it like cool and challenging. Yeah.
Yeah, definitely agree.
Yeah, totally. I like the idea of the constraints, using the constraints as, you know, yeah, you let them get pushed, but not everyone wants to. But we're talking, you're shifting to thinking as us as people, as artists and musicians. Then there's this dichotomy with the making the tools to people who are thankfully saving us having to do it. Yes, so there's always this tension, isn't there? Has Jack got a question there? You got your hand.
Hey, maybe changing gears slightly, since we've not got a huge amount of time left. I know when we were organizing the workshop, we talked a lot about what we want to do after the workshop in terms of like continuing to bring people together. And obviously we've got this Discord channel at the minute, but we may want to do something that's agnostic to a specific research group and so on. and there's talk of like a future workshop even. And I'm just wondering if, given now that we've seen all of the amazing talks today, if anyone has any comments or reflections on like next steps for this great group of researchers and hopefully others in the future.
I was wondering if and this is a question for like everyone, what's more interesting? Like, I think this format of talks work very well, but we were wondering if some format like more of like tutorials could work as well. These also, of course, I mean, tutorials can be also complex because if they're based on a specific device, then you need the attendants to have that device. But yeah, I don't know what would be useful. Or maybe a more organized repository than the Discord. The Discord server is great. There's always conversations going on, and everyone just posts stuff they do, which is great. But maybe a more organized knowledge base, or yeah. I personally think definitely a more organized knowledge base, with maybe some kind of tags or things that are searchable. You're muted, Steve. I think you were mentioning something.
Oh, I didn't press. Sorry, I didn't have the window. Thank you. This sounds like the worlds of Hello Worlds that someone talked about building in the first one. So there's lots of an ongoing organic growth of Hello World demos that people could tap into and add to and take inspiration from. I think that sounds good. This could be, how might we go about developing or hosting or something like that? Any ideas on that one?
I just wanted to say that maybe it's also also to focus in the certain devices that have been used by the research community, especially in our case for audio, like Bela is one, but the other one is also the one that the colleagues in IRCAM were using, the Jetson. Maybe it's important kind of to focus on those. I mean, the FPGAs, I really don't have much experience with it, but yeah, I mean, maybe it's necessary to focus just in certain devices, because these devices can be very different and tricky. Yeah, I don't know, because if you focus on everything, then it's too much, right? So.
Yeah, somehow we need to come up with a Discord server or a standalone Slack channel where we can sort different devices, for example, or different ideas, approaches. I think that would be great, right? We could start by doing a Slack or a Discord, a Discord server only for our embedded AI group, maybe.
Yeah, like a Discord, we have a Tensil. Sorry, pardon me. If we use the Intelligent Instruments embedded Discord channel, that's nicely adjacent to the Tensil Discord server. And then of course there's I think there's a BeagleBone Slack channel. But it would be wonderful to also solidify some of that information into a wiki or something like that. Or even just kind of a portal landing page type thing that would link you to, like Ezra's documentation of his project and the GitHub page for Rodrigo's repo and so on.
Yeah, I think a wiki would be a nice idea too. We could complement very well, like if we come up with a Slack or something for our group. Yeah.
Yeah, wiki I also think is a good idea. Actually, I was thinking to do maybe also deep learning for the Jetson, so that I compare exactly the whole thing, but with the Jetson. And deep learning, like, because these are kind of base things with all, because you have to try so many things, so many combination. So maybe it's like a test suite or something with different devices. And we could be in like a wiki or something. Because the Jetson probably has much more throughput, but there is this added latency. So, but it would be still interesting to try with the Jetson.
We are all asleep, I think.
Yeah, I've been trying to write up as much as that as I could onto the Padlet, but my typing's not that fast or accurate.
No.
So I want to apologize too. Please feel free to add to it as things come to you over there. Whilst we've still got the community together for NIME, try and put things up there. I'll go through my notes slowly as I can remember them. One quick question, actually, partly to the organizing teams. We've recorded this. I'll send you the link to download, or how are we going to, so that we want to get them onto YouTube eventually or something?
Yeah, I think the idea was to post it openly on YouTube so that people that doesn't have access to NIME, etc., can access it later and it can be shared. So if anyone disagrees also on sharing the discussion part, please let us know in private, in Slack, or in public, wherever you want, but do let us know.
All right, well, we're coming up on the hour. So thanks again, everyone who talked and everyone who came. Looking forward to hearing where all these projects are going. It's really exciting stuff. It'll be really nice to see, people trying to take on projects like Franco's and Andrea's, being able to use Ezra's profiling tools to get a sense of why that latency is spiking. Rodrigo's project continuing to grow, and then us beginning to grapple with, how do you build a user interface, and what are we doing this for?
It's great. It's been a great workshop. I'm very happy. I'm very tired too. I attended like 9-10 hours of workshop today. Yeah, in total.
So it goes.
Just came to my mind. How many people were there at the first discussion about AI that we did at NIME 2020? And did you notice how far we've gone in 2 years? Just a thought.
I didn't know this. Like, I wasn't at that NIME, but I always thought it must had been like such a great event since there's so much interest. Was it small?
In summary, no one knew what they were talking about.
Okay.
With all due respect.
Yeah. Well, thank you everyone for attending, and also the people who came twice. Very surprised. Thank you. Like the 2 sessions, I mean.